Mungu ibariki Tanzania, dumisha uhuru na umoja wake kwa waume na watoto. Mungu ibariki Tanzania na watu wake. Ibariki Tanzania, ibariki Tanzania, tubariki watoto wa Tanzania.
Are you looking at online schools that can help you to learn, master, enjoy, and apply the beauty of advanced chemistry? If that might be one of your questions, I would like to tell you that I have a good news, and possibly today you could have found a part of the answer or the whole answer for that question. How are you, everybody who is watching this program? My name is Olenjolai. I would like to take this opportunity to welcome all the local, national, and international students. And I thank God by His own grace, He has given me a gift of teaching. Teaching is me, and I am a teaching. And I'll be teaching the beauty of advanced chemistry in this program. I'll be teaching you the beauty of advanced physics, advanced mathematics, and even basic applied mathematics. So I would like to ask you to tune in into this fantastic program because we have a good news. I believe that if it's your first time, you're warmly welcome. Remember to register yourself permanently into our online advanced secondary school. So right now, let me just navigate with you with a piece of information that I've written on the blackboard. This is Tanzania Online Advanced Secondary School in square bracket OLENJOLAIM, and we have our official YouTube channel that called Tanzania Online A-Level Sec School in square bracket OLENJOLAIM, and departments, we are in departments of advanced chemistry. The subject of the day is called advanced chemistry, and this is the main topic 3, which is called the advanced organic chemistry. And we dedicate this content to all pre-form 5 students, pre-form 6 students, form 5 students, form 6 students, reciters, QT, grade 12, teachers, and chemists, who means people who love chemistry. And this is chapter 2, it's called the saturated and unsaturated hydrocarbons. And this is session 22, which is titled as Ozonolysis of Alkenes and Conversion. So conversion, we say that we end with S. So again, if you want to, I believe that any active students would like to interact with a teacher, whether online or physically. But because we are bringing this program in your house or in your school or in your car or wherever you are accessing it at this moment, or maybe in your field or in your farm, or maybe in your bedroom or in your sitting room or in your library, wherever you are. So we are bringing these programs at that place, but we would like also to interact with you regardless of the place where you are, and you are going to interact with us by using the system of writing. So it means that you can ask a question, you can give us your recommendation, you can give us the feedback about what you are going to cover with you through the comment section below. Make sure that you also subscribe if it's your first time or you forgot to subscribe in the previous, because we still have a lot to do. Advanced organic chemistry, actually, it's the longest topic in all entire advanced chemistry for the syllabus and curriculums of the United Republic of Tanzania. So make sure that you ask a question in the comment section, and I will act on you, and I will try my level best to answer your questions so that you can have a good flow. However, that I'll be trying to simplify my teaching. I'll be trying my level best. I'll be using different teaching aids. I'll be using different teaching techniques. I'll be using different teaching methodologies in order to make sure that I answer so many questions that you've been asking yourself about the topic of the day or about the unsaturated hydrocarbons, because we are focusing on alkenes. So myself, I will try my level best, but it doesn't mean that I will answer all your questions. Possibly you can have a question, or maybe you don't have a questions, but you didn't understand somewhere else, so you're allowed to ask. However, that's the promise, and I'm always trying my level best to clarify every concept that I'm going to teach to students so that they can get answers of so many questions that they have in their mind. It doesn't mean that I know the questions of my students, no, but I try my level best to answer them before they ask. But they have an access also to ask me some of the questions which are relevant. Okay, so let us start our today's session. So let us start our quick review. Okay, so let us start our quick review. So the previous session was session 2021, session 21, the previous session. So in session 21, we kept on learning about electrophilic addition, chemical reaction of alkenes. So I taught you some other examples, and the first one is we call it hydration. So one of the reactions that we taught in session, hydration of alkenes, and then the second reaction which we taught you after hydration of alkene was what? How did we name the fifth reaction?
Reaction between alkene and halogen.
So reaction between what? Reaction between alkenes, CN, 2N, and what? And the halogen, which form what? Vicinal compounds. Okay, so hydrations of alkenes form what? Alcohol, isn't it? And then reaction between alkenes and halogens form vicinal compounds. And then I began to tell you, I told you that also alkene undergoes some other chemical reactions away from electrophilic additional reaction. And hence the first reactions, which is quite different from electrophilic, we began with combustion. And we say that I told you that combustions of any alkene give us only two products, which is carbon dioxide plus water. Then the second ones we learned, we talked about oxidation of alkenes. This is the point where we ended yesterday. But we just mentioned about hydrogenation, which may be possible today. We can write short notes about hydrogenation just to remind you, but we taught you in saturated hydrocarbons because it was one of the methods of preparing saturated hydrocarbons. So oxidations of alkene. So we say that in these oxidations of alkene, the oxidizing agent is potassium permanganase. So potassium permanganase, and we say that it means that we can oxidize alkenes in alkaline medium, and the product is what? Diol, if you will remember. And then we can oxidize it in acidic medium. And in case of acidic medium, it depends now the structure of alkenes. So if you have, we can have unbranched alkene. So unbranched alkene with terminal double bond. So when we do this oxidation in acidic medium, then we say that the product is carboxylic acid, carbon dioxide, and water. Those are the products. Then we say that when we oxidize unbranched alkenes with inner double bond, then we say the products are two molecules of carboxylic acid. And we left the homework that what will be the product when branched alkene react or undergo oxidations in acidified potassium permanganate. So now let us start from correction, then we have to continue from there. And we'll be focusing on ozonolysis of ozone oxygen, then we'll be solving some problems of conversion, because we say that alkenes are more reactive organic compounds. So today, let us start with correction. Correction of homework 21. So I say that when branched alkene react with acidified potassium permanganate, so when branched, so this is just you can have a subtitle of chemical reaction between branched chemical reaction between branched alkenes with acidified potassium permanganate. So branched alkene can be oxidized, in acidified potassium permanganate to form carbonyl compounds, 2 molecules of carbonyl compounds, but sometimes it can form carbonyl compounds. Sometimes one of the product may be carboxylic acid. So the general wet chemical equation. The general wet chemical equation is when you have alkenes, branched alkenes, can be oxidized in potassium permanganate in acidic medium. And then we can have carbonyl compounds. When we say carbonyl compounds, can be aldehyde or ketones. So we can have branched alkene of this shape. The best way is this. So here we have R dash, carbon, and we have R double dash, and here we have R double dash. So these hydrocarbons, which represent them by using R, can be different. So if this undergo oxidation under potassium permanganate, then the product will be carbonyl compounds, as we say. So this one, the addition of oxygen, single dash, plus what? Now the organic compound are a double dash, then combined with this carbon, which contains oxygen, then we have the bond is R2 potassium. So that's the general reaction. So examples, CH3, double bond. So we have what? C2, H5, CH3. So we'll be oxidized with potassium permanganate in acidic medium. So this one will form CH3. CH3, then plus what? CH3, carbon double bond, CH2, H5. Here we have the phenine. Low oxidation with sulfidified potassium permanganate, then the product will be ketone plus CH2 5, carbon is oxygen, CH3. So you can note this before when alkenes react with when alkene react with alkaline potassium permanganate, when alkene react with alkaline potassium permanganate, they turn brown potassium permanganate into white precipitate. No, purple color, not brown. They turn purple color of potassium permanganate into brown color. So in organic chemistry, when reactions result on change of color, is very important because we can use that reaction, so we can apply that reactions for a particular purpose. Okay, the third example of oxidation is hydrogenation. This is no longer oxidation, it's other chemical reactions of what? Other chemical reactions of alkane, because we say in other chemical reactions of alkane, the first one is polymerization, the second one is oxidation reaction, which we have done, and the third one is hydrogenation reaction, which this we covered in saturated hydrocarbon, hydrogenation reaction. Hydrogenation reaction. Hydrogenation reaction. So alkene react with halogen under the presence of nickel catalyst and temperature of that one to form alkene. So we have taught you that alkene reacts with hydrogen, under the presence of nickel catalyst or transition element catalyst, RT, the temperature of 200 degrees centigrade. To form alkane. So just to remind you, generally we taught you that if you have alkene, react with hydrogen under the presence of nickel and temperature of 200 degrees centigrade, the product is alkane. We discussed this reaction as one of the chemical reactions of alkane, no, as one of laboratory method of preparing alkane. I think it's the first method that we discussed, hydrogenation of unsaturated hydrocarbon. So just to remind you, example, when a syn undergo hydrogenation, it forms a sun. So now when you have a cyclic compound, this and then undergo hydrogenation, the product will be cyclopropane. So, etc., etc., etc. So you can have more examples as well as we can. So now let us cover about oxidation by using ozone oxygen. So ozonolysis or oxidation of alkenes. So ozonolysis of alkenes. Oxidation of what? On ozonolysis of alkenes In other words, we call it a chemical reaction, or we call it oxidations of alkenes. This is not normal oxidation of alkenes with ozone oxygen, not normal oxygen, or not potassium or manganese that we've been discussing. Ozone oxygen. So we call it ozonolysis of alkenes, or we call it oxidations of alkene with ozone oxygen. So we have a fundamental question, this is question 1. What is ozonolysis? It's a new vocabulary. What is ozonolysis? So ozonolysis is a chemical reaction. So ozonolysis is a chemical reaction, is an organic chemical reaction between unsaturated unsaturated hydrocarbons and the ozone oxygen under the presence of organic solvent. That's the simple definition of ozonolysis. So ozonolysis is a chemical reaction between alkenes or between unsaturated hydrocarbon So what is ozonolysis? Ozonolysis is the organic chemical reaction between unsaturated hydrocarbons and ozone oxygen under the presence of organic solvent. So we say unsaturated hydrocarbons, example for saturated hydrocarbons is alkene. So alkenes can react with ozone oxygen and be followed by reductive hydrolysis and followed by reductive hydrolysis form to molecule, okay, followed by hydrolysis. So alkene can react with ozone oxygen and followed by reductive hydrolysis to break the double bond completely and give 2 molecules of carbonyl compounds. To break the double double bond completely, form two molecules of carbonyl organic compound. Carbonyl organic compound. So alkene can react to its ozone oxygen and followed by reductive hydrolysis to break the double bond, completely to form two molecules of carbonyl compounds, carbonyl organic compounds. The product depends on the structure of alkene. So the product, whether two molecules of ketones or one molecule of ketone and one molecule of aldehyde or two molecules of aldehyde, depends on the structure property of alkene. So we say that the primary structure of alkene is unbranched alkene. So we say that A, ozonolysis of unbranched alkenes. So ozonolysis of unbranched alkenes. So what will be the product when unbranched alkenes undergo ozonolysis? So when unbranched alkene So when unbranched alkene undergo ozonolysis, product is two molecules of aldehyde compounds. So when unbranched alkene alkenes undergo ozonolysis, the product is two molecules of aldehyde compounds. So the general weight chemical question is this: we have unbranched alkenes undergo or react with ozone oxygen. Some branched alkenes react with ozone oxygen and tetrachloromethane presence of water. Product will be 2 molecules of water plus aldehyde. Aldehydes. So general molecular formula we say that, for example, you have ARA like this, that's a branched alkene, or this is the one style of a branched alkene. Ozone oxygen are 3 oxygen. And then the catalyst is tetrachloromethane and water. So here we have a double bond, it breaks, from what? From ARA. Hence here we have a single bond, double bond between carbon and oxygen, and single bond between carbon and hydrogen. Last what? Carbon, double bond, hydrogen, hydrogen. So this is one of the general molecular formula.
Sir, the last carbon lacks one hydrogen.
Which last carbon? This one.
Yes.
So you should say that the last carbon is on the reactant side. Also, you can have a branched alkene of this structure. So when it undergoes osmolysis under the conditions of tetrachloromethane, then the products are CO, or let's say that O hydrogen plus R dash C double bond hydrogen and this. So examples. First example say that if example CH3 double bond and we have single hydrogen here, we have single hydrogen, or we have 3 hydrogen there, like this, 2 hydrogen like this. When we undergo ozonolysis, under the presence of tetrachloromethane, the presence of water molecule, then the products, so this bonds is going to break down, this bonds is going to break down. So when that bonds is going to break down, then we'll be oxidizing the first 2 carbons to form aldehyde with 2 carbon plus what? Even the other part of carbon will be oxidized by forming double bond with oxygen and having a single bond with hydrogen. So this bonds is the one that breaks down, and after breaking down, carbon will form the double bond with oxygen, and the other part carbon will form the double bond with oxygen, right? So these are the two hydrogens, 1, 2. These are the two hydrogens. This carbon, and these are carbons. This is carbon with its 3 hydrogens atom, and this is the second carbon here, which is forming the double bond with oxygen. So this is aldehyde, and this also is aldehyde. Aldehyde of the single carbon, aldehyde of the two carbons. It's just like methane and the methane. For the simple interpretation, because I know for most advanced secondary students, aldehyde is still a new compound for you. But again, we say that in order to have, because we can form hydrogen peroxide in this reaction, also the conditions should be tetrachloromethane in presence of water and the zinc. So we use water or zinc. And this zinc is going to be oxidized with hydrogen peroxide, which will be formed as intermediate product. It's not the final product, but it's intermediate product. Okay, so let me challenge you. This is the challenge even to myself. What if cyclopentane undergo ozonolysis? So what if this one undergo ozonolysis? We have 3 atoms of oxygen in the presence of tetrachloromethane, presence of water, presence of zinc. So what compounds will be formed? Are we going to form what? What the ketones which will be formed in this compound? Just pause the video and take just 2 minutes and then try to predict the product from this case. Because for aliphatic alkenes, okay, it's fine. So now you know the principle that the doubles will break down. Could you think that the doubles could be breakdowns and then form into aldehyde, or form into aldehyde? How will you form the two aldehyde? Because for this one, yeah, it's fine. This is the first aldehyde, this is the second one. And for this one, so you have to think. So how many carbons are there? 5 carbons. So when this when any cycloalkenes, organic compounds, undergo ozonolysis, the double bond breakdowns. But when the double bond breakdowns, also the other 2 double bonds will be formed, but not the double bond between identical atoms. So it will be the double bond between carbon and the oxygen. But remember that ozonolysis actual conveyed cycloalkenes, organic compounds, into aliphatic or straight chain organic compounds. So what does it mean? When this bond break, just like here, then we are going to have an open structure. You have to see. So this open structure will be having this carbon. So let's say that here we have carbon 1, this is carbon 2, this is carbon 3, this is carbon 4, this is carbon 5, for your understanding. So let me start with carbon 1. So carbon 1, they are double, so when it breaks, then it's going to form a new bond with oxygen. But this one carbon, carbon 1, just double bond with carbon 2, and also it has a single bond with carbon 5, and it has hydrogen. So it still has its hydrogen. Then we have carbon 2. Okay, so there's a single bond between carbon 1 and carbon 2 because this bond is broken down. So this is carbon 2. No, excuse me. So this is carbon 1. So when you write this is carbon 1, then we come this is carbon 5. We have a single bond between carbon 1 and carbon 5. Then the carbon 5 itself, just this number, let me just write first. Carbon 1 itself, there's 2 hydrogen here, one there and the other one's there. Then we have carbon 4. So it has also 2 hydrogen, 1 hydrogen, 1 hydrogen. You have to be careful with these ozonolysis reactions because they are often being asked carbon 3, then there's one hydrogen there, and there's one hydrogen, then you have carbon 2. So carbon 2, we have double bond with oxygen and single bond with hydrogen. So this is our final product. So this one is carbon 1, this one is carbon 5, this one is carbon 4, this one is carbon 3, this one is carbon 2. That's why I say that ozonolysis of cycloalkenes compounds open the structure and convey it, and it's formed kind of aldehyde. It's still aldehyde, but aldehyde with two functional groups, right? Because this is just the functional group of aldehyde, is the second functional group of aldehyde. So if you want to challenge yourselves more, think about this. And then when it undergoes osmolysis, so complete, do this practice under presence of tetrachloromethane, presence of water, and then the presence of drinking catalyst. So you have to be careful. That's why that you would like to see our students are competent in learning, mastering cycle of organic compounds, because sometimes they can deviate from the normal product that students expect when the same organic molecule undergo the same organic reaction. Okay. So let us focus now on branched alkenes. So ozonolysis of branched alkenes. So ozonolysis of branched alkenes. Ozonolysis of branched alkenes. So ozonolysis of branched alkenes. So branched alkenes can be oxidized with ozone oxygen. Branched alkene can be oxidized with ozone oxygen under the presence of water and zinc metal. Form either two molecules of alkenes, from two molecules of alkenes, from two molecules of ketones. Form two molecules of ketones or one molecule molecule of aldehyde can be one molecule of ketone. So it can form, so the reactions can result to molecules of ketones, or it can react to one molecules of aldehyde and one molecule of ketone. So it depends. The structure of the branched alkenes. So general word chemical equation. General word chemical equation. We have branched alkenes. Ozonolysis. No, that is ozone. Ozone, oxygen, and presence of tetrachloromethane, presence of water or zinc metal. So as we say that the product can be two molecules of ketones, or depending on the structure, the branched alkene can react with ozone oxygen and tetrachloromethane, presence of water and zinc metal. And this can form one molecule, one aldehyde plus one ketone. So general molecular chemical equation undergoes ozonolysis in the presence of tetrachloromethane. So the product, in this case, the products are two molecules of ketones. Two molecules of ketone. So here we have R single dash, and yes, here we have R double dash, R triple dash. So this is R double dash, and this is R single dash, and here we have R triple dash. So just the bond breakdowns here, because here we have that bond, and this hydrogens is no longer there. So these double bond breakdowns, it forms ketones, another molecule of ketone. But if we have a single branch E or single branch like this, then CH, then I have R double dash, so we have tetrachloromethane, presence of zinc, oxygen, this is ketone. Also we have another molecule of aldehyde. So if you have a single branch, then the product will be one molecule of ketone and one molecule of aldehyde. If you have two branches of alkenes, the product should be two molecules of ketone. That is, so it's nothing difficult. So if you have one branch, products will be what? One molecule of aldehyde and one molecule of what? Ketone. If you have two branches, products product will be one molecule of aldehyde. No, two molecules of ketones. So let us start from here, CH3. So this one undergo ozonolysis. Under tetrachloromethane, in the presence of water. So these double bond breakdowns. Stop writing. So CH3 double bond is oxygen. CH3 oxygen CH3. But if you have CH3, you have a single branch here, like this, and it's a double bond, and here we have two molecules of hydrogen. When this one undergo ozonolysis under presence of tetrachloromethane, presence of zinc and water. Now these double bond breakdowns. Stop writing. These double bond breakdowns. When breakdowns, these form ketone, one molecule of ketone, and this form one molecule of aldehyde. Okay?
Yes.
Simple like that. So here we have CH3, then we have that bond with this oxygen, then here we have C2, H5, plus what? So we have that bond with oxygen, single bond with hydrogen, single bond with hydrogen. So let us think about when branch D, cyclobutane, undergo ozonolysis. So the bond break, you have double this. So suppose this is first carbon, second carbon, third carbon, fourth carbon. Have to be careful for ozonolysis of cyclo compound. So here you have double with oxygen, FCH3. So it is still ketone and aldehyde. So this part is aldehyde, this part is ketone. This is first carbon, this is second carbon, this is third carbon, this is fourth carbon. Okay.
Yes.
So simply this double bond breaks down. Okay? So when it breaks down, this carbon will form double bond with oxygen, and the fourth carbons will form also double bond with oxygen. This is the branched. Okay. Are we together?
Yes.
Okay. From session 19, I think from session 20, I told you alkene is a very reactive organic compound. And you can see that it undergoes so many reactions more than alkenes. The first example, keep on challenging you. What if you cyclo compounds? And here we have and the undergo ozonolysis under presence of tetrachloromethane, presence of water and zinc. So now we have branched the cyclohexene. So look how the bonds will break. So the simple way for you to avoid contradiction, name this as your first carbon, your second carbon, your third carbon, your fourth carbon, your fifth carbon, your sixth carbon. Okay. Then think how the bond will break down and oxidations will take place. So you may start writing the first carbon here. Right? Right?
Yes.
So the first carbon, first of all, it has some 220 group, attached group, which it is cyclohexene. So it has, there's what? So let's say that here there's a bond with cyclopropane. So this is cyclopropane, this group. Right? And then it had double bond between carbon 1 and carbon 6. So these double bonds break down. So when it breaks down, the cyclo compounds open and become a straight chain. Okay? So when it becomes a straight chain, this double bond between carbon and carbon will be replaced with double bond between carbon and oxygen. Are we together?
Yeah.
So again, but this carbon, the first carbon has a single bond with the second carbon, and the second carbon carries its hydrogen atoms. Then there's a single bond between the second and third carbon, and the third carbon carries hydrogen atoms. Then there's a single bond between carbon, the third carbon and fourth carbon, and the first carbon carries the hydrogens, and there's a single bond between the fifth carbons and the sixth carbon, and the six carbons or the fifth carbons carry the hydrogen atoms. So then we are in 6 carbon. So the 6 carbon, it has its substitutive group, which is CH2 or C2H5, right? So this is the 630 carbon. First carbon, second carbon, third carbon, first carbon, fifth carbon. No, wait, made a mistake. First carbon, second carbon, the third carbon, fourth carbon, fifth carbon, sixth carbon. So the sixth carbon also had a double bond with this first carbon, which just breakdowns through ozonolysis process. So when this double bond of the sixth carbon will be replaced with double bond between carbon and oxygen. Are we together?
Yes.
So this will be the product that will be formed when maybe one SI hyphen 2 cyclopropyl hexene undergo ozonolysis under presence of tetrachloromethane in presence of water and zinc.
What is the name of the product?
The product. Yeah, so you learn when we'll be naming about your carbonyl compound, because this is the carbonyl compound, this is the ketone. Yeah, so there are principles you have to follow and rules to name carbonyl compounds. It's not a topic that I'm teaching you, but just to inform ketones are the hidden in mid-distill or 40 of the chemical reactions of alkenes. Okay?
Yeah.
So they should. So you have to be careful, because in conversions or in the next session, in the next part of this session of session 22, I'll be giving you some questions which you have to write the reactants while we are giving you the product. Are we together? Right now we are moving from left-hand side of the chemical reaction to the right-hand side. Later on, so we'll test you, we'll give you what are the products on the right-hand side of the chemical reaction and ask you to give us the reactants. So you have to be careful and you have to pay attention, especially for the cycloalkene, ozonolysis of cycloalkenes, organic compound. Are we together? Okay. So let me write the following note. 2 notes, and then we'll go into the questions. First note. When I'm branching the alkane and I go ozonolysis in absence of zinc. Then the intermediate hydrogen peroxide, zinc metal, then the carbonyl compound So when a branched alkene undergoes ozonolysis in the absence of zinc, so the carbonyl compound formed will be oxidized by hydrogen peroxide from carboxylic acids. Form carboxylic acids. For example, we have phenyl propane, so when it undergo chemical reaction with tetrachloromethane in presence of water without zinc, then the product will be benzoic acid plus what? CH3 or plus ethanoic acid. The intermediate product before oxidation, because of the absence of zinc, will be this. So when this, stop writing. When these aldehyde, because this is the aldehyde aromatic compound, when these aldehyde aromatic compounds undergo oxidation under the presence of hydrogen peroxide, which is intermediate product, then this aldehyde will be oxidized by this oxidizing agent to form benzoic acid. Form benzoic acid. So just like this. Plus. Also, if this one, in the absence of zinc, will be oxidized under the presence of hydrogen peroxide, then the product will be CH3. This one will be what? Ethanoic acid. So this is extra oxidation. Ozonolysis is first stage oxidation, but because we don't have zinc, like in other reactions, so zinc always reacts with zinc with hydrogen peroxide to form zinc oxide at the function of zinc in ozonolysis of alkenes. So in the absence of zinc, then alkenes or branched alkenes undergo further oxidations to form what? Carboxylic acid. And this is an excellent example to show you. This is aldehyde, this is aldehyde. But when it is undergone further oxidation with hydrogen peroxide, which is the intermediate product, we have benzoic acid, we have ethanoic acid. So you have to be careful. All of those reactions should be kept in your mind. You should not confuse them step to step. You have a lot to do. So let me write the second note and then we'll go into the question of profession. Profession. So the second note. The products of ozonolysis of alkenes, of branched alkene, the products of ozonolysis of branched alkene, the products of ozonolysis of branched alkene can be used to reduce branched alkene can be used to reduce the structural formula. Can be used to reduce the structural formula of alkene. That is undergone ozonolysis. As I say that, sometimes it can give you products of ozonolysis, and then we ask you that to give us the reactants. So it means that you can use the products of ozonolysis to reduce ozonolysis of branched alkene, reduce the structural formula of alkene that has undergone ozonolysis. How? So I told you, if one of the product is aldehyde, then it is what? Single. If the products of ozonolysis are two aldehyde, that's unbranched alkene. If the product are one molecule of aldehyde and one molecule of ketone, that is single branched alkene. So branched unbranched and the branched alkenes. So we have three products we expect. If the products are two molecules of aldehyde, that's unbranched alkene. If the product is one molecule of aldehyde and one molecule of ketone, that is single branched alkenes. If the products of ozonolysis of alkene is two molecules of ketone, then that is two branched alkenes. Two branched alkenes. So this makes what? We added an example, 11 or 12. I'm asking you, local student. We ended an example. Ah, 12. Maybe example 11 was the homework. Give original structure of alkenes with the following. Give the original structure alkenes, use the following compound. Use the following compounds. Okay. CH3. Okay, so we have been asked to give the original structure of alkenes. Use the following compounds. So from an A, you have to check. So you've been asked just to give the original structure of alkenes. Use the following compounds. So the first one you have to check, and the second one. So you have two molecules here. So you have to check them, and then you have to say, okay, you have to state that which product or which reactants has undergone ozonolysis. You are not asked to mention that which type of reactions, but you have to understand that whenever you have those two molecules, you have to know which organic or which reactions of alkene can give you two products of this organic compound. So the question is not clear that maybe alkenes undergo ozonolysis and form this and this and that. You should know in your mind which reactions of alkene that give you two molecules of this functional group. Right?
Yes.
So you have to, even if that you don't know anything about carbonate, about carboxylic, about whatever, just you have to remember the simple definition that I've been giving you. For example, this one, whenever you have a terminal hydrogens, or whenever you have a terminal double bond between carbon and the oxygen, that in organic we call it aldehyde organic compounds. All aldehydes have terminal double bond between carbon and the oxygen. That's what should be a terminal. When you say terminal, it means the double bond at the end. Right?
Yes.
That's why its functional group we use right this way. At R, then we have double bond between carbon and oxygen, and single bond with hydrogen. So that the functional group for what? For aldehyde. Bear it in your mind. Whether you know anything about carbonate, but this you should know. Because alkenes actually that accelerate you to know the structural formula of carboxylic, structural formula of carbonyl compounds, structural formula of alkynes, structural forms of alkane, of alcohol, of alkyl halide. So alkene will accelerate you to know different structural formula. So when it comes to this one, whenever you have inner double bond between carbon and oxygen, that molecule is what? Ketone. Whether you know its name, how do we name it or not. The point should be in your mind, this is ketone, this is what? Aldehyde. Why this is aldehyde? Because there's a terminal double bond between carbon and the oxygen. Why this is ketone? Because there's inner double bond between oxygen and carbon. If you refer session point, I began to introduce you about inner double bond of unbranched alkene and the terminal double bond, or unbranched alkene with terminal double bond. So that is common language in organic chemistry. Right?
Yes.
So now we have aldehyde. Don't bother yourself. When I will teach about carbon and compounds, I will teach you how you can name each of these. These are very simple to name them. Don't bother about the year names, right? Just to go straight forward to the questions we have been asking. So this is an aldehyde, and this is what? A ketone, right? So you know which chemical reactions of alkene give us these two products. Is it combustion? No. Is it electrophilic addition? No. Is it hydrogenation? No. Is it oxidation of potassium permanganate? No. Because oxidation of potassium permanganate, okay, kind of it can give us, but sometimes it's a little bit depend on the structure, right? And it depends also whether in acidic medium or in basic medium, right? So this is all about ozonolysis of unbranched. Is it unbranched or branched? Branched alkene with a single branch. Why? Because we say in branched alkenes we have possibility of forming two products. One aldehyde, one ketone, or two molecules of ketone. Right? So here we have one aldehyde, one ketone. I told you. So it's just a revision of what I've told you. So now, how these molecules have been formed? So there is double bond of branched alkene which has been broken to form these two molecules. So right now you have to formulate. So you say, okay, so on product side it means that I have what? I have CH3, I have this double bond, terminal double bond between carbon and oxygen. Then I have ketone, CH3, then double bond with this, and then I have CH3 here. Something like this, isn't it? Huh?
Yes.
So then I know that these products will be formed. The condition is presence of tetrachloromethane, the presence of water, and the presence of zinc metal to avoid further oxidation. So if that's the case, this is CH3. So you can start writing this one. Then we have carbon. And here we have hydrogen. So here we have double bond. So this double bond which has been formed, originally it was a double bond between this carbon and this carbon. So we have double bond here with this carbon. You can even number your carbon. Maybe it's the first, second, third, fourth, fifth for you to be sure. So suppose that this is the first carbon and this is the second carbon. So there's a double bond between second carbon and fourth carbon. So we have a double bond. So this is the first carbon. But again, you have first carbon attached with what? Attached with. So the first carbon formulated a single bond with the third carbon, this one, right? But also they formulated a double bond, no, single bond with the fifth carbon. So this one. So 1, 2, 3, 4, 5. Okay? So this one has undergone ozonolysis from these two molecules. So for Roman A, say that the structure of original, so the structure of original, the structure of alkene, original structure of alkene, or the structure of alkene, the original structure of alkene, original structure of alkene is, so you write it, CH3 can formulate maybe your longest chain, then you have CH, okay, or you can have, okay, CH, then you have what, FC, then you have CH3, Then you have CH7. So this is the structure. Here we have that one. That's why that we have such kind of a bond. That's the answer for Roman A. So for Roman B, again, let us assess. Is this aldehyde compounds, stop writing. It is an aldehyde organic compounds or ketones organic compound? Look on the blackboard, please. Is this an aldehyde organic compounds or a ketone organic compound?
Ketone.
Huh?
Ketone.
How many of you say that that is ketone? Raise up your hand. How many of you say that that is aldehyde? So you? Why didn't you raise up your hand? Okay, so this is ketone. Why it is ketone? Eh? Because of inner bond. Did I say that because of inner bond? Why this is a ketone molecule?
It is ketone molecule because the double bond is not bonded to the terminal.
No. You have tried, but it's not right. I say a ketone organic compound has inner double bond between carbon and the oxygen. Don't mention inner itself or terminal. It's a terminal double bond of what? We have so many different types of what? Of double bond in organic chemistry. So when you say just double bond between what? Sulfur and oxygen. So this is the ketone molecule. Is this an aldehyde or a ketone molecule? Huh?
Aldehyde.
Okay, some of you say aldehyde. So, how many of you say that this is the aldehyde? Raise up your hand. How many of you say that this is not aldehyde? Okay, so you are right. This is an aldehyde. Right?
Yes.
So which reaction of alkenes, or which is original structure of alkenes, give us one molecule of aldehyde and one molecule of ketone?
Branch there.
Which branch the alkene. Okay, yeah, the answer is right. Branch the alkene of which structure?
Phenyl.
Huh? Phenyl. Branch the alkenes of which structure? Because you have two structures of branched alkene. I say we have single branched alkene and they have double branched alkene. Single branched alkenes give us two products, one molecule of aldehyde and one molecule of ketone. Double branched alkenes give us two molecules of ketone. You didn't understand from there, so try your level best to understand what you have here. Be careful, listen, write, listen, concentrate, think. Don't copy and paste. We are not teaching you how to claim this stuff. We are trying our level best to use a simplified language so that you can understand and master them and apply them for the rest of your life. So CH3, and then the other one is an aldehyde molecule. So this is the product. To form, what are the conditions required to form one molecule of ketone and one molecule of aldehyde for ozonolysis? You forgot. While everything is still on the blackboard. Condition is under presence of tetrachloromethane, in presence of what? Presence of water and zinc metal. So what is the reactant? Look, how we formulate the reactant. So the reactant is simple. I told you the principle. We have phenyl as substituent group. I say stop writing. When I tell you stop writing, you have to stop writing. If you will keep writing, you won't understand and then you get confused later on yourself. So CH2, and here we have double bond with oxygen. So originally there was a double bond between this carbon and this carbon. So I told you in order to avoid confusion, you can number your carbon first, second, third, fourth. Simple, right?
Yes.
So there was what? A double bond between the second carbon and the first carbon. That bonds undergo ozonolysis. That's why that now we have what? Ketones and aldehyde. Okay?
Yeah.
Okay, so this is the first carbon, this is the second carbon. So we had what? Double bond between the what? The first, between the second and the first carbon. So the first carbon carrying what? 2 hydrogens. So it's carrying 2 hydrogens. So this is the third carbon. But we have first, second, third, fourth. So we have a double bond between second and first, but the second bond also has a single bond with third carbon. Right?
Yes.
So this one, it is an allonology, ozonolysis, and form this product. So, answer from B, the original structure of alkene is here phenide, CH3, here you CH2, then CH3. The original structure of alkene.